Powerful collaborations, cutting-edge science, and curious minds coming together for a glimpse of the future. Stay tuned as we look at the latest updates on some of the most promising technology projects. Welcome to our program. I'm Peter Ballant from Technicon, and today we are talking about the FutureTPM project once again. As the name implies, this project is all about preparing for the future. To be more specific, we're talking about the future of cryptographic security in computing. To understand the importance of this project, you should know that cryptographic security is a cornerstone in our modern world. It's simply everywhere, and this includes in the TPM, or Trusted Platform Module, that keeps your laptop safe, or the server that transfers your bank data. TPMs are ubiquitous, and why? Because they work. But they won't always work. You see, quantum computing is coming. Computationally, quantum computers are exponentially faster than anything we know. Today's TPM can't possibly perform in this environment. The FutureTPM project is the proactive approach that will help ensure that today's TPM algorithms will work in a post-quantum world. In other words, FutureTPM is contributing to the quantum-resistant TPM. Today we are joined by Thanassis Giannetsos from the Technical University of Denmark. He's a technical lead in FutureTPM. Thanks for talking with us today. And here we are talking about FutureTPM again. Tell us, what's it all about?
This is a project that mainly tries to create new security protocols in the context of trusted computing that will be able to also operate correctly in the post-quantum era. What we mean by this is that we all know, or most of the people know, that in the next, I would say 10 to 15 years, quantum computers will be available. This means that most of the traditional cybersecurity algorithms and crypto primitives that we are currently using are going to be broken. And the main reason behind this is that the keys that are being used in today's crypto primitives are not strong enough, are not big enough to be able to withstand quantum computers. So this is one of the main motivations behind this project, is to actually do the research and do the investigation of creating, designing, developing, and also testing new quantum resistance crypto algorithms that can also be integrated in small computer chips, which are called Trusted Platform Modules, TPMs. TPMs is one of the main enabling factors in the context of trusted computing. So basically, what this means is that it's a hardware chip that can provide the root of trust to the host device that it is embedded. It provides functionalities like enhanced crypto operations. It can enhance the crypto operations in terms of how fast they are executed. And it's one of the main enablers nowadays that is being used in a lot of application domains, or at least we want to migrate to decentralized solutions where root of trust are getting closer to the edge devices. For instance, if we have connected vehicles, which is a very hot topic nowadays, we want to be able to have trust closer to the edge. Up until now, we were having a lot of centralized solutions, which basically means that we were relying to the backend infrastructure to provide us all of the necessary security mechanisms. So we are now in the process that we want to transform this type of centralized ecosystems to more decentralized environments where we are having root of trust in various places. TPM is one example of such a hardware-based token. Of course, we also have other similar tokens, but TPMs, it's one of the most prominent examples. And TPMs, for instance, nowadays come on board into many of the of the new day, let's say, laptops and computing systems. So the idea is that the quantum resistant algorithms that the project FutureTPM is investigating, we also want to be able to put them in the context of a TPM. So think of it that we want to create the new generation root of trust that will be able to cope with quantum adversaries. So in the context of the project, we are also designing new quantum resistance privacy preserving algorithm, and we are testing them and putting them in the context of the TPM. And we are lucky enough to also have on board Infineon from Germany, which is basically one of the main vendors of TPM chips. And they are also helping along with the integration of such algorithms inside the TPM chip and how this looks like.
To sum this up, we could say that the TPM is really a quite effective way to secure hardware and software, but there's a threat coming, and this threat is quantum computing, and this is coming in the next 10 to 15 years, and it's not too early to start thinking about how will a TPM react in such an environment. It sounds like there are parts of TPM that can't withstand the power of the quantum computer, and you and your team at the FutureTPM Project, you're looking for answers. You're sort of rebuilding the TPM, so to speak. Would that be correct?
Exactly. So these are the two main technological axes that the future TPM revolves around. One is on developing and investigating quantum resistant algorithms, and the other thing is how to be integrated into the TPM chip. This can be considered as actually providing this type of a new root of trust that will be able to cope with quantum adversaries. If the root of trust is able to cope with quantum adversaries, this means that it will be able to also offer this type of enhanced security level for the whole computing system that is hosting the TPM. But this goes beyond the TPM. If we prove and we showcase that such algorithms can actually be integrated in a small resource-constrained device, this is a key enabler so that we can actually be able to start putting quantum-resistant algorithms inside various application domains. So what we are trying to do is that we are actually trying to showcase that, yes, you can have the level of security needed for the quantum-resistant aspect, but you can also put it in a resource-constrained device.
You're the technical lead of FutureTPM. What is your part in the project then?
So I am one of the scientific coordinators of the technical leads. We are working together with Professor Likun Chen from University of Surrey. That is also one of the other core partners in the consortium. Due to the complexity of the project and the fact that we are covering different aspects, we decided at the beginning, where we were formulating the proposal, to have two technical leads in order to be able to collaborate and have a better monitoring of the entire progress of the project. So my main role in the project as one of the technical leads is to be able to coordinate specific aspects of the research activities that are being done in the project. The main separation basically we're doing is that Professor Lee is a very well-known researcher and she's dealing a lot when it comes to the quantum resistant aspects of the project, and I'm monitoring a lot of the activities when it comes to the integration to the TPMs, the trust computing, and how the solutions we are creating can also be evaluated in the context of specific application domains. So we have a number of use cases. So I'm monitoring and coordinating a lot of the research activities in this domain.
We're going to get back to the use cases in a little bit, but I wanted to ask you also, aside from the obvious technical advancements, how else does this project impact the EU in terms of the type of research that you're doing?
That's a very, very interesting question. And it's always in the context of such big European projects, it is very important to also showcase how we are advancing not only the state of the art when it comes to the technical artifacts, but also the position of the EU. One of the main points here is that, as I mentioned before, there are different working groups around the world that are working towards quantum-resistant algorithms. And we have standardization bodies within Europe, within the US, and also within China. The main standardization body that is driving this process is NIST, which is a US-based working group. So by having this project done within Europe and European partners, we are actually strengthening the position of Europe when it comes to having access to quantum-resistant algorithms and have the necessary expertise to also be able to take the next step, not only designing the algorithms, but also implementing them and integrate them in very resource-constrained devices, which this basically allows the actual usage of these algorithms in various application domains. So it puts the EU at the same level, especially with US, or even further beyond, because it provides this expertise of the implementation. Another important thing when it comes to the application domains and the position of Europe is that we are having a lot of discussions when it comes to Internet of Things, industrial Internet of Things, green energy, smart cities, smart homes, and so on and so forth. So we are actually living in the era where we are trying to automate a lot of processes. We are having so many devices, so much data, and everything is connected. In order for this type of systems to be secure, we need to be able to have very strong decentralized security protocols. The decentralized here is the keyword. In order for us to be able to actually do this, then we actually have to be able to have this type of root of trust that we are talking about, which is basically a TPM. So we are increasing the readiness of Europe when it comes to being able to have this new generation of TPMs that will be readily available to be integrated in this transition that we are talking about, moving towards having so many connected devices. So we can have devices where they are hosting this new generation of a TPM. So we are increasing the readiness of Europe to be able to have a much stronger security protocol for safety critical application domains. These are the two main impacts that I see when it comes to the position of Europe within the crypto domain and the trusted computing domain.
One can see why the Europeans would invest in such a project like this. This will put us at the forefront, essentially, of cutting-edge technology.
Yes, of course. And the good thing, if you see the history in the last couple of years of the investments that Europe has been doing in this type of projects in the context of quantum resistance, it's quite substantial. So think of it that the future TPM can be considered as the last part of a trilogy when it comes to the European calls that they have opened for getting proposals and projects in this domain. So there was one project at the beginning called PQ Crypto, and this was actually a very successful European project that created a lot of the new algorithms, quantum resistant algorithms that have progressed within the NIST standardization body. Then we also had another project called Safe Crypto, which focused also in different design and implementation issues. And now we have FutureTPM that takes the next step of creating new algorithms and actually put them in a resource-constrained device like a TPM. And even together with us, like at the same time, there are other projects. There's another initiative called Prometheus that is focusing even more on privacy-preserving algorithms. So you can see that Europe is putting a lot of effort, that is investing a lot of resources towards this direction of strengthening its position in the post-quantum era.
Yeah, and you're a part of it. That's great. When you look at a consortium like this, part of the strength comes from the diversity. So I'm wondering, in FutureTPM, what kind of makeup do you have? Is it research institutes or is it academic? Or generally speaking, what's kind of the makeup?
It's all of the above. I have to admit we are very lucky in our consortium that we have some of the most well-known professors, universities, academics, and research institutes. So in general, our consortium comprises of a mix of universities, big industrial companies, SMEs, and research institutes. So when it comes to universities, we have, as I mentioned before, University of Surrey with Professor Li Kun Chen. She's one of the pioneers in crypto, and also her work in the trust computing domain. It's very well known. She was the one that also wrote the specifications for TPM 1.0. We have Infineon, which is the main vendor in Europe when it comes to the TPM chips. We also have University of Birmingham. They have very well-known expertise in formal verification. We have a number of SMEs from various European countries that have come on board to provide us with specific use cases. So they have products that are actually deploying, and in some cases, they're also selling. And we are using their infrastructure to be able to do our testing. So in this context, we also have Huawei from Germany. We have an SME called Shoot5 from Cyprus. We have another company from Greece called Indev. And INDEF basically it's one of the, let's say, key companies that is dealing with electronic payments in Greece. So they're collaborating with the bigger banks in Greece. We also have research institutes like Ubitech from Cyprus. So Ubitech, again, it's a quite well-known research institute that provides expertise in risk assessment, trust computing, attestation, and so on and so forth. So I'm sure I'm forgetting a couple of the partners because we have too many partners, but you can see we have a very good mix of research-oriented people and industrial people. And of course, let me not forget that we also have IBM, and IBM is being doing like they are at the forefront of providing new quantum-resistant algorithms at NIST. So we have all the necessary attributes that we need to be able to complete successfully such a complex project.
Yeah, it sounds like a great consortium and perhaps a reason why you've been so successful to this point with FutureTPM.
I have to be honest, we were lucky with the consortium. We have actually collected the best of the best, let's say, in Europe in their field.
So this leads me to my next question, which is on the website, it says that the project ends at the end of this year, at the end of 2020. So what happens with this momentum that you've built? Are there follow-up projects, or is this knowledge that you've gained, is this used in some way by another group, or is it published? And then what happens to all of your work?
So again, I would say it's a combination of many of the things that you also mentioned. Most of our work, when it comes to the algorithms and the integration to the TPMs, they have already been published as scientific papers in the context of the last almost 3 years. Yes, we are going towards the end of the project, which is end of 2020. So most of our work has been already published, which means that the algorithms are there, and the algorithms can also be used by other people in the research community to be able to keep on doing their research. So I think this is a very important thing, because basically this is what, for me, research is about. Okay, research is not reinventing the wheel. It's us building blocks, so we are actually progressing one step. We are putting our work out there so that other people can actually build on top of it and keep on creating new algorithms and keep on doing new evaluation and tests. Another important aspect that we have already started discussing, based on the results that we have gotten so far and the feedback that we have gotten from the community, but also from the EU, is that we will try to actually put forth new project initiatives based on the output of FutureTPM. Again, it's a good thing, and it seems that the EU is very interested in quantum computing related aspects. FutureTPM is part of the current EU project framework, which is called H2020. This framework also ends at the end of the year, but it has already been released, the new framework that will run for the next 5 years, which is the FP9. If someone goes and reads the topics and the calls of the FP9, there are already plans by the EU of accepting new initiatives in the same domain. So there is again, like now, a very strong direction towards combining the outputs of many projects to be able to start creating a quantum testbed that we can actually start using and testing our algorithms. So we're in discussions, and hopefully the plan is to be able to keep, as you said, the momentum that we are having, and submit a new initiative that will enhance even further the output of the FutureTPM. Another important direction, because of the SMEs that we have on board, and as I mentioned, a couple of the SMEs, they are actually brought in the project their products and their solutions and their services. The idea is to also keep on testing and actually have not simply proof of concepts that we have now, but even try to roll out a first version of the new generation of a TPM in one of these solutions. Of course, this will not be in the context of a hardware-based TPM, because we are having like a proof of concept implementation. The project is not creating the actual new chip, but we will be able to actually roll out and test in real-world settings the artifacts of the project. And last but not least, Infineon is actually using the output of the project in order to keep pushing their research in creating the new chip. Okay, let's say we are now having TPM 2.0, so potentially to roll out TPM 3.0, which will be able to have these new quantum resistant algorithms.
Okay, so yeah, you give some great examples of how this research will go on, and it sounds like the EU is committed to keep the research going until the day that quantum computing is knocking on our front door.
Exactly. And because again, as I agree completely with you, we have a very, very good momentum. And to be honest, based on the first set of results that we have gotten in the project, they are very promising in terms of the resources being used by the TPM, the timing. So the evaluation and the assessment of that we have done. We want to build on top of this and keep on pushing the research and keeping Europe like at the forefront of the quantum resistant post quantum era.
And finally, from the point of view of the technical lead of this project, what can you tell us about lessons learned? Many times in a project there are things that are unexpected, and it requires a certain course of action to keep the project on track. So is there anything that sticks out for you that was unexpected or that you had to deal with in a rapid kind of way to keep things on track?
That's very true, and especially when we're talking about such a complicated, complex project. So, of course, there were a couple of bumps that we had to overcome. I cannot say that they were completely unexpected. The main goal is on the investigation of quantum resistant algorithms. And the project, in order to be aligned with what has also been done in the standardization working groups, we were always monitoring what was happening, in working groups like NIST, like ISO, IC. So the main working groups that were dealing with quantum resistant algorithms. So NIST currently has started for the last, I think, 4 or 5 years. It's like a competition when it comes that it opens some calls for the community to start submitting their proposals for quantum resistant algorithms. They allow for the publics to verify the correctness of the algorithms, or if they manage to identify vulnerabilities, which basically means that the algorithms are not considered quantum resistant, and only those that are not we have not identified vulnerabilities, they can progress to the next round. So currently we are in the third round of NIST, and we actually reached this round, I think, in August this year. A couple of the algorithms that we had selected based on the previous round, they actually did not progress to the final round of NIST. So we had to make a couple of updates and align our suggestions to also consider what has been proposed by NIST. And as you can understand, this was like a continuous process because we had to monitor what was happening by other standardization bodies. And this started actually from the end of the first year, that there were a couple of vulnerabilities identified for some of the algorithms we had selected, and we had to make the necessary updates in our suggestion, which means that also when it comes to resources, we had to implement new algorithms that were proposed. So this was one of the main challenges of the project. And of course, another challenge was to be able to identify overall security protocols based on the use of a TPM, irrespectively now if we are talking about the quantum resistant TPM or the current TPM, that will convince also the community that this is the way to go, okay? Of how to be able to showcase that by having a TPM at the edge, providing these new functionalities, this have a better output in terms of the security posture of the overall system itself. I would say these are two of the main challenges, but due to the very good coordination we had in the project, also when it comes to putting all of the partners together to discuss these things, we were able to identify mitigation actions very, very quickly.
And that's the best you can hope for in a project like this. I mean, there's always something unexpected, but how you deal with it really determines in which direction the project goes and how. So, yeah, I want to say thank you for sharing a little bit about FutureTPM with us. It sounds like it's a successful and very meaningful project for the citizens of the EU, and we look forward to seeing what happens in the end. We can connect again at that time. It would be interesting to find out once the project ends how things came out.
Thank you very much for the invitation, and thank you also for setting up the podcast.
Yep, we're happy to do it, and we'll check in again.
Of course.
For more information about the FutureTPM project, visit futuretpm.eu. This podcast has been brought to you by Technican. This project has received funding from the European Union's Horizon 2020 Research and Innovation Program under Grant Agreement number 779391.